Welcome. My name is Aleksandar Zeljic, and I will present some ongoing work in formal methods at the Stanford Center for AI Safety. Here we can see the team involved in the work that I will present today. The team is led by Clark Barrett and consists of 2 postdocs and a PhD student. And we have an ongoing collaboration with Guy Katz at Hebrew University of Jerusalem. The problem that I want to discuss today is that of verification of deep neural networks. Given a neural network and a property, we want to check whether the network exhibits said property for all possible inputs. In this talk, we consider fully connected feed-forward neural networks with piecewise linear activation functions. We can see an example of such a network on the slide. 2 types of properties are of interest. A reachability property can be seen on the left, and it says that for any input in a given range, the output will not be in an unsafe range. Reachability properties often stem from a specification of a network. On the other hand, when a specification is lacking, we are interested in exploring robustness properties. As shown on the right, a robustness property says that given a fixed input-output pair, denoted by bold X and Y on the slide, all inputs within the delta distance will result in the same label. Inputs that violate this property are known as adversarial inputs. So, how can we actually show these properties? Since the connections between the layers are linear, if we disregard activation functions for a moment, we can solve the linear relaxation using the simplex algorithm. We can see an example on the slide showing a small simplex tableau and its satisfying assignment, which is highlighted in the yellow row. Since this is a relaxation, the satisfying assignment needs to be checked against the piecewise linear constraints. Here we have 2 ReLU constraints, and we can see that the blue ReLU constraint is satisfied by the assignment, since both variables p and r are positive and equal, while the red ReLU is violated. We now have 2 options. We can adjust the assignment to try and satisfy the ReLU, or we can guess a phase for the ReLU and add its constraints to the linear problem. In this case, let's guess that the broken ReLU should be in the active phase and add that the equality between variables s and t to the problem. Such guesses, as well as any related inferences and backtracking, are handled using the S&T techniques. Using this new information, the simplex can now find a new satisfying assignment for all the constraints involved. The algorithm I just illustrated is implemented in Marabou, a solver for neural network verification. It implements ReLUplex, an extension of the simplex algorithm with native support for ReLUs, combined with lazy splitting. The algorithm was originally proposed by Guy Katz in 2017. It is sound and complete and supports piecewise linear activation functions such as ReLUs, max, sine, etc. Marabou also implements a split and conquer algorithm. It's a meta-algorithm that breaks down a solver query dynamically based on the provided effort limit. It can be tailored in a variety of ways and is particularly amenable to parallelization. There will be more words about this algorithm in a few slides. When we consider how Marabou is used in practice, 2 scenarios emerge. Input-output verification of a network, which we consider as analysis of a snapshot in time. Here we have reachability and robustness properties as examples. Or we also can do analysis of the network over time as part of some larger system. This usually involves techniques such as model checking and adaptive stress testing. Regardless of what type of application we're talking about, such as robustness verification of a perception network or querying the solver on the fly to find adversarial examples, a reliable and conclusive analysis may require millions of solver calls in practice. To rise to this challenge, we focus on improving the overall performance of the Marabou solver through improvements to the algorithms implemented by the solver, improvements to scalability, for example, through parallelization, but also by finding smarter ways to pose queries to the solver, by either reusing the information of subsequent or incremental queries, or by bundling similar queries together, for example, using hypercubes to reframe multiple robustness queries. When we talk about improvements to Marabou itself, we're working on several different things. Improvements to pre-processing and in-processing techniques, which are crucial for timely inference and collapsing the search space, come to mind first. We use triangular relaxation of ReLUs, such as used by MIP Verify, as well as symbolic bound tightening, which was first proposed by ReLU and Verify. With backtracking search, memory footprint and maintenance overhead is critical. And here we resort to a number of different engineering approaches. For example, trying to fix the size of the tableau to avoid reallocating memory when new information is added, using data structures for sparse matrix representation, as well as lazy backtracking data structures such as those used by the state-of-the-art SAT and SMT solvers. Finally, the more complex a solver, the more choices are being made. So we are always looking at reassessing various heuristics involved in the process. Now let's take a look at the split and conquer algorithm. Suppose that we want to solve formula phi with some initial timeout t1, and the solver query times out. So we can split the query into 4 new ones, for example, if we have 4 cores at our disposal, and try to solve each of them with a larger timeout t2. Suppose that 2 of those formulas, phi1 and phi3, are now shown to be unsatisfiable. However, 2 other formulas still time out. Now we can split these formulas in turn and solve each of them with a larger timeout. The algorithm will stop when either all generated subformulas are shown to be unsatisfiable, or if we find one satisfiable subproblem, such as the formula phi23 on the slide. Split and conquer algorithm has several parameters that allow the user to shape the search. For example, setting the initial timeout and its growth rate between generations regulates how aggressively we want to split the problem, while the number of splits in each generation will regulate how fine-grained the queries will become. One very important question for the algorithm is how to generate the next generation of problems. One approach is to split the input range, which performs well on networks with few input parameters, such as AKS-X. However, it struggles with high-dimensional neural networks, which is not really surprising, for example, since splitting a value of a single pixel is not very consequential for the output of the network. In that case, we may instead want to split on early layer ReLUs instead, which are often far fewer in number. Regardless of the method chosen, splits are performed in a way that results in balanced divisions in terms of input space size. On the right, we can see polarity, a metric that we use for this purpose. U and L denote upper and lower limits, and they are respectively positive and negative because they have to contain the decision boundary in between. And the smaller polarity scores are considered to be more balanced. Finally, to avoid repeated preprocessing for each subquery, we use iterative propagation. It guesses a phase for individual ReLUs, and if the query quickly returns unsat, then the ReLU can be fixed to the opposite phase. It is a parallelizable, effort-limited preprocessing step, which can fix up to 20% of ReLUs using interval propagation only in practice. Now let's take a look at the impact of parallelization on performance. The scatter plot shows runtime of sequential Marabou on x-axis and split and conquer algorithm on the y-axis. The solid black lines denote the timeout of 1 hour, and lines that are parallel to the diagonal denote speedups of ×2 and ×8, respectively. The benchmark set consists of a mix of reachability queries and AKS-X benchmarks, as well as robustness queries on the MNIST and TaxiNet models. Points below the main diagonal show instances in which the parallel approach performs better in terms of runtime. We can observe that the parallelization benefits instances with high sequential solving times, and in particular, many which are unsolvable using the sequential approach to begin with. We can see these instances clustered on the vertical timeout line. Given these results, we were curious how far can we actually push the parallelism? So we used the GG platform to deploy the split and conquer algorithm to a cloud computing service, AWS Lambda. The service allows up to 1,000 tasks with up to 15-minute workload each. In the plot, we can see the average query runtime shown on the y-axis, and on the x-axis, we can see the increasing number of workers allocated to the queries. The benchmark set used here is a subset of the ACAS benchmarks. We can see that the runtime is decreasing as we increase the number of workers, with only a hint of the diminishing returns in the very last step. Overall, we take that these results show that there is a lot of benefit to leveraging parallelization for verification of neural networks. Now I'll switch to some ongoing work. We consider generalization of sum of infeasibilities, which is a standard simplex technique for guiding the search. We want to generalize this technique to the piecewise linear context. So given an assignment, sum of infeasibilities denotes the amount by which an assignment X violates the constraint bounds. We can sum the difference between the variable assignment and the violated bound to obtain an error function, which can then be added to the tableau. Minimizing the SOI represents an effective search strategy for linear problems, because once the sum reaches 0, it actually means that every variable is within its bounds, which indicates a satisfying assignment. We're wondering whether we can extend this idea to work with ReLU functions, right? So the definition of a violated bound can now be extended to include different ReLU phases. However, the resulting function is going to be nonlinear, and therefore it cannot be easily added to the tableau directly. Instead, what we want to do is choose a linear approximation, which will only be correct for one chosen ReLU phase. The challenge now lies in how can we actually use this linear approximation of SOI to guide the search. And given that the SOI, nonlinear SOI, is not monotonic, the algorithm will not necessarily terminate on its own. So we will need to use some other methods that are available in Marabou to ensure termination. Another direction of work that we're pursuing is leveraging set-solver-style conflict analysis in Marabou. When simplex detects infeasibility, a subset of conflicting constraints can be extracted using the Farkas lemma. Most of these conflicts will be implied by ReLU decisions, which are essentially Boolean. So we can then use a SAT solver as a conflict database, which will detect previously seen conflicts and prune the search on the fly. Over time, the SAT solver may even be able to extract enough Boolean structure from the problem to infer knowledge about ReLU decisions based on past theory reasoning. We hope that closer integration of SAT and SMT techniques will lead to better explainability of decisions of neural networks and also certifiable proofs for neural networks. To conclude, we're addressing the challenge of increasing the solver performance for the purposes of analysis of real-world neural networks. We have seen some of the ideas that we pursue in this direction, which involve improvements to the solver itself, from algorithms and data structures to heuristics, as well as finding new ways to pose queries in a more scalable fashion, using parallelism and hopefully incrementality in the future. Finally, we saw some of the ongoing research ideas, such as leveraging conflict analysis and nonlinear sum of infeasibilities. Another recent work that I didn't really include in the slides here is that on adversarial optimization. It involves modifying the default search of Marabou to optimize the adversarial examples so that we can find either the minimally violating or the maximally violating adversarial examples. The reference can be found at the end of the presentation. There is also ongoing work to support additional activation functions as well as new formats such as Onyx. Marabou is available from GitHub at the shown address and will be demoed as part of the event on January 13th. Here you can see the list of references that have been used throughout this presentation. Thank you for your attention.